So as an overview about this presentation, I'm going to talk a little bit about what RFID is, some misconceptions about what are the components of an RFID system, what kind of security implications do we have, how does an RFID software stack look like, how do readers look like, how do drivers look like for RFID readers. So RFID in general, as obviously all of you will know, is a radio frequency identification used for numerous different purposes, including transportation sector, retail sector, government areas like the biometric passports. RFID is really much more a buzzword than a word specifying a particular technology. So in the world of RFID, there is hundreds of different protocols and different implementations of those protocols and so-called standards that are not really standards, but just some proprietary vendor-based schemes. So everything is, if people think of RFID protocols like internet protocols, then there's a misconception because most of the RFID systems and protocols in use are actually quite proprietary and little documented. So in an RFID system, we have a tag, sometimes also referred to as transponder, which can have specific nature. So there's very easy tags or transponders which just have a serial number that can be used as a replacement for, instead of a barcode, a European article number kind of label, stuff like that. There's write once, read many tags, which you can write once but read many times. So it's not just a fixed serial number, but a serial number that you can program yourself or whatever kind of number. There are read-write tags, which is basically like a synchronous memory card, contact-based, but not with a contact-based interface, and instead having a radio frequency interface. There are read-write tags with passive security, which means that they implement some kind of security features, cryptography, for example, access control, permission handling, and so on, but it's all implemented in a state engine, so there's no microprocessor on that device. And then last but not least, we have systems which are also called RFID, but which in reality are cryptographic smart cards with an RF interface. And the latter category, cryptographic smart cards with RF interface, is what we have in our electronic passports, for example. So RFID is basically, in the context of passports, it's just the RF interface glued to a cryptographic smart card. So it doesn't, if people talk about RFID, they mostly talk about these stupid, dumb transponders that are only, read only, read write, whatever kind of things. We also have readers. They're always called readers, even though they do write. It's quite interesting. Anyway, so yeah, it's like with smart cards. I've never heard somebody speak about a smart card writer. Anyway, they come in lots of different kinds of interfaces. Most of them either RS-232 or USB interface for host computers. Some of them have other protocols like RS-485. And the like. Recently, we're also seeing readers that directly hook into Ethernet as their uplink interface. Unfortunately, there are no standards and no standard APIs whatsoever. So every reader has a totally different command set. It's a totally different device, which has its different registers, its different commands, different modes of operation, and so on. This is very different from the contact-based smart card world, where now, at least for USB devices, we have the CCID standard, which is a USB vendor-independent standard for driving and talking to contact-based smart card readers. But for RFID, no such thing exists till today. The RF interface that actually exists between the transponder and the reader is also quite different in various ways. Milosch is going to talk about that in more detail, so I'm going to go quickly over that. It's just important to know that there are different RFID systems using different frequencies, different modulation, different operational principle. The operational principle that we see most often is called magnetic coupling. So basically, the information interchange and the power transmission between the tag and the transponder uses a magnetic field. And it's used on frequencies such as 125 kilohertz and 13.56 megahertz. Mostly the 13.56 megahertz systems used today. Operational range is often quite small because it's a magnetic field, not an electric field. There are other operational modes or systems that can be used. One of them is backscatter. which is not really all that much deployed yet. Another operational principle works by using surface acoustic waves, and they use microwave radio signals, and basically in totally different frequency bands, so it's microwave based. But the systems we usually see in today's life are all magnetic based coupling. A couple of standards, real standards as in openly documented international standards that we have in the RFID area are listed here. There's ISO 11784-785, which is used for identification of animals. So for example, here in Berlin, if you register a dog, then that dog has to have an RFID transponder implanted in case the dog is found somewhere or whatever, that the owner can be located and so on. That's what is being used here. It's very low bandwidth, 4,000 BPS, but well, how much do you need? It's just some unique number to identify the owner of the dog. There's an extension which allows you to put more data into that. It's called ISO14443, and then there's a standard that almost nobody knows of. It's ISO10536, which is close coupling up to 1 centimeter, which is not really very practical. I mean, if you need to be as close as 1 centimeter in order to make the device work, then you can use contact-based interfaces in most places anyway. I mean, no point on using an RF interface over the distance. Then there's currently under development the ISO 18000 series, which is quite a lot of talking going on about this right now. Sometimes the industry usually refers to it as the Auto ID standard. Auto ID basically is intended for replacement of barcodes and these kinds of systems which we currently have for product and package labeling and these kinds of applications. The ISO 18000 series is a series of standards because it basically specifies high-level protocol operations on the foundation of a number of different low-layer protocols and on different frequency bands, different modulation schemes. So it can be used in all kinds of different technologies, from microwave to 2.4 gigahertz down to the 13 megahertz magnetic coupling. As I know, there are no real deployments of that yet, but that's what we're going to see in the future. Currently, what we see quite a lot in RFID cards is either ISO 14443 or ISO 15693. ISO 14443 has a specified operational range up to 10 centimeters. It comes in two variants called A and B. Mainly, who was A? Well, B is basically the French Postal Service's proposal or protocol, and A is, I don't know which vendor it was, but as it happens in the smart card industry quite a lot, when they get together in order to found a standard, then neither of the 2 or 3 big vendors in the field want to change any of the existing products and just want to have their existing products specified as the international standard, and then we end up with 2 different variants, A and B. Both use 13.56 megahertz, but very different parameters. There's a paper which is certainly going to be linked from the CCC homepage accompanying this presentation where there are some more details about this. The ISO 14443 specifies the physical layer, link layer. Link layer mainly means anti-collision. When we talk about anti-collision in RFID, that means we need to somehow distinguish between multiple transponders within the reach of the magnetic operational field of a device. The speed can be up to 848 kilobits per second, which is quite high. And this speed is actually being used with the electronic passports in order to achieve sub 2 seconds border control timeframes, because you need to transfer, you need to do all the cryptographic handshake, and you need to transfer some 20 to 30 kilobytes of JPEG image within 2 seconds, and then you need quite high baud rates to get that job done. Especially considering the latencies that exist with these small microcontrollers. Anyway, ISO 15693 is called Vicinity coupling, specified as up to 1 meter. It's like ISO 14443, operates on the same frequency band, has a two data rates, a slow data rate and a little bit faster data rate. but because they operate over such a huge distance, huge in as magnetic field over 1 meter is quite a distance, and they can only have very little power. So as to my knowledge, there are no smart, as in smart cards or any kind of cryptographic and so on, transponders available for ISO 15693, just because their power requirements of any kind of sophisticated processing would not be possible in the magnetic field over the distance. So it's mainly used for passive tags, for the stupid serial number kind of tags. So let's look a little bit closer at ISO 14443 A. The anti-collision is based on a binary search algorithm, and it's using a Manchester encoding on the magnetic radio link in order to detect bit collisions. So Manchester code has this this property that in the middle of each bit clock there is a level change from either low level to high level or high level to low level. And basically, if two parties or two transponders transmit at the same time and they transmit a different signal, then you can sample at the first bit half and the second bit half. And if you have the same signal, then there must be two transponders sending, because there always needs to be a high-low or low-high transition in the Manchester encoding. So by using this kind of encoding, the reader can actually detect whether there's only one transponder transmitting a signal or multiple transponders are overlapping their signals onto each other, and bit collisions happen. So the reader can detect this by using that. So what each of these transponders have is a unique serial number, UID, PUPI, whatever. There's multiple names floating around, and the reader needs to basically select a transponder. And by using a binary search algorithm over the whole, let's say it's just theoretically, let's say it's a 48-bit ID, and then you can basically, the reader says, well, you can imagine it as net masks, for example. So you can say that the reader requests a /0 net mask in all the tags which in reach will reply. If there's only one tag replying, then the reader will detect that because there's no bit collision. Every tag will transmit its serial number. Serial number needs to be unique. So if there are two tags transmitting, they have two distinct serial numbers. The two signals will overlap, will cause a bit collision, which can be detected by the reader. If the reader detects a bit collision, then it basically says, well, I want all tags with a specified prefix within the serial number, including the bit where the collision has happened, to respond. And if there were only two in the field, then only one of them would reply. And then you do a binary tree search over all the existing tags in order to select individual tags or transponders in that. And there's this looping algorithm over there. Obviously, this is one of the first possibilities for any kind of exploits or security kind of issues, because if you create a tag that causes always bit collisions at every bit position, then the reader will be unable to select any tag that exists in the field. ISO 14443B has a different bit anti-collision system. It's called a slotted alloa protocol, and it's based on a probabilistic scheme. So basically, the reader can, on its so it can define time slots, can say now time slot 1 starts, now time slot 2 starts, and so on. And every transponder, when beginning an anti-collision cycle, chooses a random number that is modular the number of time slots that the reader advertised. And just by statistic probability, it is likely that multiple tags will respond in different time slots and not in one. If they respond in one, the whole thing starts all over again. Again, we have the easy ability to interfere with this mechanism by always causing collisions and by causing retries, and getting into problems in here. So for both A and B, we can do denial of service blocker tags. They have been demonstrated. I haven't built any, we haven't built any, but it's possible to do so, and we'll certainly be able to demonstrate that at some point with some own hardware as well. Another system that is very commonly used is called MyFair. It's mainly a marketing term by Philips. It's very confusing when you get into that kind of industry or business or technology and you want to learn about it. everywhere there's MyFair here, MyFair this, and sometimes they refer to a protocol, sometimes they refer to transponders, sometimes to a specific chip or another chip, but it's all MyFair, so it's very confusing. So basically it's a complete family of RFID systems, including protocols, encryption specifications, including ASICs for readers and so on. So everything is just called MyFair. What they have is basically they have a compatibility up to, it's based on ISO 14443 and layer 1 and layer 2, which is the physical layer, well, the RF interface, and the anti-collision is the same as ISO 14443/1 and /2A. But the higher level protocols are proprietary. So they always claim, oh, we have this standard-based RFID system, but yeah, well, you know, it's like calling some proprietary protocol that operates on Ethernet standard-based because it uses Ethernet as the underlying infrastructure. So the main thing when you talk about MyFair is what is now referred to as MyFair Classic, which are transponders, memory transponders with state machine-based crypto. So this particular category which I was talking about. No processor, but some state machine that implements some crypto. This crypto algorithm is called Crypto 1. It's a proprietary stream cipher. I think it's 48-bit key length or something like that. It must be cheap to implement because the MyFair tags, they are used in very high volume of applications such as electronic ticketing, these kinds of applications. So it's not possible to put some expensive integrated circuits in there. So it must be something very easy to do. And in order to create security, the algorithm is just not documented. So it's a security by obscurity kind of thing. It didn't really work with the cipher used in GSM. It didn't really work with WEP. It sort of fits into a similar category of ciphers. Anyway, so the way the system works and the way they create vendor lock-in is by putting the hardware crypto implementation of this cipher into both their reader ASICs, the chips that are used by most vendors of RFID readers, and to put the same crypto algorithm into the transponders themselves. So when you have a Philips reader ASIC in some reader, doesn't have to be from Philips, and a MyFair RFID transponder, MyFair Classic compatible RFID transponder, then both of them have this proprietary crypto embedded, and you can have this proprietary security. There's another variant called MyFair Ultralight, which doesn't have any crypto. It's a plain passive memory transponder. MyFair Ultralight is what is being used in the Champions League football tickets last year. So there was no cryptography involved whatsoever. And no form of authentication or anything. I'm interested in what's going to happen next year in the World Championships if they're going to use MyFair Ultralight again, because there's no encryption, no authentication, so you can very easily create duplicates of that, for example. Anyway, the MyFair transponders themselves are segmented into blocks of memory. The size of the block and so on it depends on the particular transponder. Every block has its own Crypto 1 key. So the idea of this system is that you can use one RFID transponder and allocate one block to each application that you use this card in. So you can use the same transponder card for public transport and for accessing your, whatever kind of access control at doors, at the company, and so on. So basically you can, by having a single card that can have lots of different blocks, which each have their own encryption keys, you can use it for multiple applications. There's also a public MyFair application directory by which you can inquire. So if you have an MyFair RFID card, there are application identifiers on them which identify the application that this card is being used for. And you can query that application directory. It's basically just a table that you can download from the Philips website, and you will know, what kind of system this card is being used in. It's quite convenient. Anyway, a closer look on readers. There's a variety of readers in this 13.56 megahertz world. Some of them only speak a specific protocol. The more modern ones speak all of the 13.56 megahertz based protocols. So the modern reader ASICs, they speak ISO 14443A, 14443B, and 15693, and all the proprietary protocols that are based on these standards. There's most of the readers actually use some of the available ASICs. So instead of developing the whole reader yourself, you just get an ASIC from TI, from Philips, from wherever, put that onto your PCB, and it implements the analog front and the digital back end. Basically, it implements everything. So just put that ASIC on a PCB, add some 2 capacitors, and then you're done. The end user readers you typically contain an additional microcontroller that interfaces with USB or whatever kind of external interface. There's 2 categories of readers that you can find in the market. One of them are active readers that implement the RFID protocol stack, 14443, anti-collision, and all these kinds of things, in the reader firmware on the microcontroller. And there's another category of readers which implements that on the host system, on the PC or whatever kind of system you use. And the reader is just a stupid, you can say, well, transceiver or something like that. And the whole stack runs on the system. Obviously, the latter ones, the passive readers, are the ones which you can have more fun with, because it's your software that runs on your computer that you can control easily, that you can use your regular development tools, that you can debug with your regular development tools, and so on. So that was the way I went for the LibRFID project that I'm just going to talk about next. Some security issues. There's certainly eavesdropping. We did some sniffing on RFID. Milosch is going to talk about that in a couple of minutes. Denial of service, as I said, the anti-collision mechanisms used in those common protocols, they are all very vulnerable. Authenticity, confidentiality, well, there's very little, actually. Okay. So the LibRFID project is basically a project that aims to implement 14443 and 15693 ISO standards in software on a PC or whatever kind of hardware that you can attach a reader to. It's written in C, currently only tested on Linux, but should work on about any operating system that libUSB runs on, because the supported readers are only USB readers. I've also started to add support for MyFair, for example, recently. So I'm trying to add more and more protocols that I can find any kind of documentation or find the time to reverse engineer them. So for example, on MyFair, you don't get any kind of documentation because of all their obscure, security by obscurity kind of thing. Even though the crypto is implemented in the hardware, you still don't find the documentation for how to actually talk to the ASIC. Anyway, it integrates with OpenCT. If you have been using smart cards on Unix-based systems, you might have heard about OpenCT. It's a package which contains a number of drivers for various contact-based smart card readers. And basically, LibRFID interfaces with OpenCT to add support for currently only 2 different, or let's say 1.5 different readers. Both of them I have here. This is basically an OmniKey, what is it, 5121, and the Philips Pagoda reader. So OmniKey is fully supported, Pagoda is currently in the works. This you can get for about 70 euro, the other one is about 200 euro. And they use the same ASIC, so you pay for the Philips name probably, or whatever, for the stylish design, and the blue LEDs, it has blue LEDs. I think even 5 of them or 6. Anyway. Which you can control by using documented commands over USB. So if you look in the documentation of the reader, there's actually documented how you switch on and off the LEDs, but it's not documented how you talk to the MyFair. Anyway. So there's a number of structures. I'm not going to go into too much of detail here. Basically, there's a struct RFID ASIC, which encapsulates the object of such a reader ASIC. There's an ASIC transport, which encapsulates the transport used between your piece of program that runs on the PC and the ASIC that runs inside or exists inside the reader. So usually there's some form of USB communication or serial or whatever kind of communication. Every vendor uses a slightly different kind of protocol here. So you can have, for example, these 2 readers, they use the same ASIC, but they use totally different transport channels over USB, and that's why there's this abstraction between having an ASIC and having the transport channel. And there's an RFID reader, which is basically groups a transport channel and the ASIC together, and then there are layer 2 and higher layer protocols. And layer 2 currently working ISO 14443 A and B, and higher level protocols, ISO14443 and MyFair at the moment. 14443 is it's quite interesting. You could say it's not really like TCP, but still it has quite interesting features. So if you think that this is a dump memory card or whatever, a dumped card that you're talking to, ISO 14443 has acknowledgements, negative acknowledgements, retransmissions, and so on. So there's basically stuff like fragmentation. There's stuff like, so it's a real transport protocol that ensures guaranteed delivery, ordered delivery, and so on. So there's really quite some similarity between network protocols and this ISO 14443. So the typical stack you will have when running LibRFID is basically at the bottom you have libUSB that gives low-layer user space access to USB devices. On top of that you have the USB CCID driver for OpenCT, because this device here is actually a contact-based reader that you can put contact-based cards into, and also a contactless reader. So the contactless card you can obviously just put here or put it in. It doesn't really matter. It just has to be closed. So it's a contact-based reader, and that's why I'm using the CCID driver. So you can use the contact-based part of the reader first, and then on top of that there is some encapsulation for accessing the RFID part of the device, and then the CLRC623 ASIC, that's what Philips calls this ASIC in there, and the CM512 on reader object, and then the real protocol stack implementing the higher layer protocols on top of this. There's currently only fully supported a native API, which is an API that is specific to LibRFID. You will not find on any other RFID system. It's quite low level and requires lots of knowledge of the application about RFID, which it shouldn't need to know. I'm working on integrating with PCSC, CT API, and OpenCT, so you can use common APIs that are used for contact-based smart cards as well with contactless smart cards. Okay, so there's now some information on electronic passports, which I'm going to skip. How are we in the time anyway? That's not it. Okay. Okay, the electronic passport stuff, I'm just going to skip that. I just want to point out, since Starbuck did an excellent presentation on that subject just 2 hours ago, I just want to point out that there's a libMRTD as well, which is sort of a sister project to libRFID. Sorry, it's MRTD, not MTRD, there's a typo in there. MRTD is Machine Readable Travel Document. It's the official acronym for what we call an electronic passport. So what you get as an electronic passport is actually an ICAO compliant MRTD. Including an MRZ, by the way, but not an MRV. Anyway, you can write a whole glossary about those terms they use in this passport world. It sucks. Anyway, so it's a library for machine-readable travel documents. So using this library, you can basically do almost as much as if you've seen that application that Starbuck was demonstrating on Windows, the official Golden Reader tool, libMRTD implements all the low-level functionality for doing basic access control, for doing the challenge response key handshake, for doing the transport level encryption between the passport and the host system. And libMRTD can be run on top of libRFID, and then you can write some application, or there's also a demo program which you can use to actually read out the JPEG image and the other data from your passport by only using free software. Okay, there's APIs for that. So we can, for those who are more into the passport thing, we can read the logical data structure, data group 1, data group 2. There's parsing function for CBEFF, the ISO, I forgot the number, shit. The ISO protocol for the common biometric encoding, whatever format, I forgot it, encoding file format or something like that. Anyway, slides for this presentation you will find here. There's also a paper which I presented originally at Linux Congress. That's why I have this LK 2005 URL here. The libRFID code you can find at the given URLs. So if you're interested in it, look into it. There's almost no documentation. It's in an, I would say, not alpha anymore. It's already in a beta stage, so you can use it. It does useful work. You can read out passports. You can read out MyFair cards. It does work, but it's not fully integrated smooth with GUI tools or stuff like that. It's still a bit whatever. Not very smooth yet. But anyway, it works quite well with a number of cards. So if you're interested in that, check out the code. patches are always welcome. There's a mailing list, there's a homepage. Yeah. Thanks for your attention, and I'm going to hand over to Milosch, who is going to talk about the passive surveillance part.
Oh, ja, gleich. Hello, I'm Milosch Meriac, and I will talk about passive RFID sniffing. I'm a freelance hardware and software developer living in Berlin, and the problem we are looking at is reading passively the transaction between reader and tag. This sounds simple in the first place, but in fact there are several problems. The first problem is that it's an inductive coupled protocol. The RFID device is powered by the protocol, and the first problem we see is that everybody says that you can, for example, access this RFID cards only within a distance of 30 centimeters or less. This is not true for passive sniffing. The point on passive sniffing is that you don't need the power supply feature. You have, in fact, three parties. You have the reader, you have the tag, and you have some kind of antenna which sniffs the transaction. So only the tag has to be powered and within the 30 centimeters distance, but your sniffing party can be further than that, because the sniffing party can be powered by your own power supply. We want to stay cheap, so everybody can use this technology to reverse engineer protocols. Harald already said that there are hundreds of protocols, and we want to make it possible for everybody to build his own sniffing hardware and to reverse engineer the protocol he wants to see. First, I want to introduce you the basic hardware approach, so it's more clear how the sniffing actually works. On the left side, you see the reader. The reader generates the carrier frequency at, in this case, for ISO14443 13.56 megahertz. Can you decrease the volume a bit for the microphone? Test. And the carrier is received by the tag by using a transformer approach is similar to transformers. You have two coils, and it's very same like transformers. You don't have the coil that connects it, but you have an open magnetic field. So the tag receives the field. You see C1 that it's connected on the tag, and make sure that we are resonating to the field, so you can make sure that you have the highest possible output. You see also the part with D1, C2, and Z1, which gets the power supply part of the signal. Basically, it's a simplified schematic you see here. Normally you have a bridge rectifier, so you get more power. In this case, you only get the upper part of the wave, and it's basically rectified with D1. It's smoothed by using C2, and Z1 makes sure that the chip doesn't die because if we get too near to the reader, because you can get several hundred volts coming out this schematic. And the sending part of the reader is simply amplitude modulation of the carrier frequency. It's well known. You just decrease the amplitude of the sender signal, either by a given amount of percent, which is specified by different standards, or you completely pull it to 0. This is the receiving part. You also can see that after D1 you always get the power supply, but the data can be still seen independent of the power supply. The question is how does the tag send its data back to the reader? A common misunderstanding of RFIDs is that the RFID chip sends the data actively like a radio transmitter. This is not true. You see it you see the MOSFET below R on the tag side, and this is used to introduce some sort of shortage. So you get actually a higher load on the tag side, on the reader side, because the reader needs more energy to keep the magnetic field up. And if the send line is triggered in this case, you get this shortage, and you see an amplitude change on the reader side. And on the reader side, you see this BP part of the schematic, and the BP makes sure that only this amplitude change is filtered out of the signal by a bandpass, and it's demodulated. The basic idea of modulation is that if you, in this particular case, you have this 13.56 megahertz, and you have an additional carrier of 800 kilohertz, and this carrier is, for example, turned on and turned off. And this is modulated onto the 13.56 megahertz by using amplitude modulation. The resulting signals look like this. If you add this 800 kilohertz, you get two sidebands on the which you can see on the reader side of center frequency F0 and this 847 kilohertz. The reader and this 800 kilohertz frequency on the tag side is turned on, turned off by the given baud rate. There are several baud rates. One common is 106 kilohertz. So this 847 kilohertz shifts around this F0 plus 847 kilohertz plus minus 106 kilohertz. So in fact, you see this diagram, and if you want to see the data transmission coming from the tag to the reader, you actually have to look at the sidebands. One big sniffing problem is that the distance between the back channel and the carrier signal is at least 50 decibel. This is very high, so you just can't take the signal with a common antenna, amplify it, because you will increase the noise, and you still have a very big distance between the signals you are interested in and your main signal. So the only approach that is possible to see the back channel is to filter it out and then amplify it. The part reader to tag is, as I said, more simple. You just have 106 kilohertz, and it's added directly to 13.56 megahertz, and you get two sidebands of 13.5 megahertz plus 106 kilohertz and minus 106 kilohertz. So the sender part is very simple, and what have we done to actually get the signal? What we didn't want is to buy expensive antenna equipment. You can't use the existing electric antennas, you need a magnetic loop antenna. Magnetic loop antennas are awfully expensive, but we found out that's only because of one thing. The point is that the magnetic loop antennas you can buy freely and they're expensive are used for sending also. You need very expensive adjustable capacitors for this kind of antennas because we have very high voltages when sending. But we only want to sniff passively, so we can use cheap capacitors, and it's very simple to build a homebrew loop antenna. The simplest possible loop antenna is by you can achieve is by buying a plastic hula hoop, get a thick, really thick copper wire, 2 mm does the job, a very cheap adjustable capacitor, and a toroidal core to create the interface to your BNC and your further processing equipment. And you just build it that way. Below you see the adjusting, and above the tuning capacitor where you tune the device to the resonant frequency you are listening to. What we have done, we used a commonly available RF down mixer where we take this 13.5 megahertz and mix it down to a frequency where we get freely available filters. The point is filters are only available at very few frequencies, so it's practically not possible to have custom ones built. So we have to live with this disadvantage and tune it to a frequency where we have filters available. We found the combination of filters by using, or possible filters by taking the 13.56 megahertz. We want to have a look at the sideband at plus 847 kilohertz. And we took a commonly available 3.6864 megahertz crystal and used this to down mix it to 10.72 megahertz. Why 10.72? Because at 10.72 you get very cheap commonly available ceramic filters. For example, at a bandwidth of 400 kilohertz or so. So you can see both modulation products of the sideband. This is how it looks like. Basically, you see the chip that does the down mixing. You have the crystal that creates the 3.68 down mixing frequency, and you have in the lower picture you see a 9-volt battery and a linear regulator which creates the 5-volt power supply, and you have a high-speed op amp that buffers the signal, so you can do everything you want with the resulting signal. These are the schematics. This is the current signal. You get a clean reader to take data output, for example, which you can demodulate or do whatever you want with it. But it's absolutely clean. You don't have any noise because everything besides of our signal is filtered out. So what do we want to achieve? We want to add the simpler part, in this case, the reader to tag sniffing into one device, so you can do a full duplex sniffing. So you see both parts of the communication at the same time. You don't have to switch actively. So we have full duplex. We want to increase it to distances to 3 or 5 meters. This should be possible by using this hula hoop antenna. TCP dump-like toolset is being created, and what is very very simple to do. You've seen it on the slide where the tag and readers working mode is shown. We have just to add one MOSFET to create a back link to the reader, and we can very easily emulate tags. The point is, we can emulate every kind of tags with this device. Then you don't, because we don't need to have an eye on our current, because we have our own power supply. We can use a high-speed microcontroller, and which can be freely programmable and is freely available. So you don't have you don't need some special controllers, and you only have to implement a software stack, and you can emulate every kind of device with this. What can it be used for? You can replace lost RFID tags. You can you can reverse engineer unknown protocols. There are plenty of them, already told. You don't need physical access, neither to the reader nor to the tag. You can, for example, stand in a row, and someone 1 meter in front of you or 2 meters in front of you is using his RFID card, and you can sniff the communication passively and post-process it on your home computer as you want. You can try offline key cracking. You can validate a self-built RF interface. Or what is also interesting, if you have, for example, some gate and people are passing through and RFID tags are read, you can passively collect the same data which the RFID gate sees. So you are in full control of people passing through the gate. You see their RFID serial number, and you can create a protocol. So any questions?